All right, so welcome to the live stream. I have a few calculus type questions to work on with you tonight. Of course, if any of you are watching and have some other questions that you'd like me to go through, feel free to send them over to mathquestionshelp@gmail.com. So give me a couple seconds here. I want to grab a couple limit questions to work on with you. Okay, so let's work on the following three limit questions. We'll start off with the limit as x approaches 3 of x plus 3 divided by x plus 6. So the first thing I always do when I come to a limit question is I look to see if I can do a direct substitution. So that means, am I allowed to actually just directly substitute 3 into here? Do I run into any problems when I do that? So in blue, I'm just going to work through kind of my thought process. I'm going to sub in 3 into the numerator and 3 into the denominator, and I'm going to get 6 over 9. So in this case, because I don't have division by 0, I don't have to look for some kind of alternate strategy to solve this limit, and direct substitution is going to be perfectly fine. Now, an interesting thing can happen if, let's say, I change this limit just a little bit. Let's say I say, let's say I have the limit going towards -3. And I'm going to keep f of x the same. So I'm going to keep it as x plus 3 over x plus 6. I can still work through this process of thinking about direct substitution. In this case, I'll get -3 plus 3 in the numerator and -3 plus 6 in the denominator. So is direct substitution going to be okay for this particular limit? Absolutely yes. I'm going to get 0 over 3, or we think about this as 0 divided by 3. And 0, as long as we don't divide by 0, we're going to get 0 as our final answer here. So 0 in the numerator is okay. It's when we start getting zeros in the denominator, when we work through direct substitution, that we have to think about alternate strategies. Okay, so next up, let's look at this limit involving a square root of x. So if we can't use direct substitution, I'm kind of thinking in the back of my head that maybe working through a conjugation might be helpful. So let's go ahead and do a direct substitution of x is equal to 9, and just let's see what kind of mentally happens. So I'm going to get root 9, which is 3. Subtract 3 in the numerator. So the numerator is 0. And in the denominator, you're going to see that 9 subtract 9. So I'm going to get 0 over 0. So that's not particularly good. Means we should look at developing some kind of strategy to help us with this limit. And like I said earlier, because I see a root sign in here, I'm kind of automatically thinking maybe conjugation is going to help. So I'm going to multiply by the conjugate of our numerator. Okay, like this. So I'm really just multiplying by the number 1 here. And hopefully this conjugation is going to help us. Okay, so let's work through the numerator. The numerator is conjugate pairs. So one of them has a subtraction sign and one of them has a plus sign. I'm going to end up with root x squared subtract 3 squared. I'm going to end up with a difference of squares in the numerator after everything is said and done. And if you need to expand out and get all 4 of your terms, and you're going to notice that the 2 middle terms are going to disappear. Now essentially I'm looking for something in the denominator to cancel out. So I'm going to leave my denominator in factored form. And you're going to see here when we go to simplify our numerator, we're going to get x subtract 9. And we're going to be able to cancel out that factor in the denominator. So just a general piece of advice when you're working on your limits, if the denominator is factored, you're probably not going to expand the denominator. You're probably going to keep it in factored form, and that's going to help with the cancellation of one of these factors. Okay, so now we have the limit as x approaches 9. Our new numerator is 1 because of this division of x minus 9. And our new denominator is root x plus 3. So now I can do a direct substitution of x is equal to 9, and I'm going to get 1 over 3 plus 3, or 1/6. Okay, let's work through one more limit together. Here we have x squared minus 6x plus 9 all over x squared minus 9. So again, I'm going to come into this question, I'm going to start thinking about direct substitution. So if I sub 3 in, I'm going to get 9 minus 18 plus 9. So my numerator looks like it's going to be equal to 0. And my denominator is going to be 9 minus 9, which is also 0. So again, I'm going to get this indeterminate form, we call it, 0 divided by 0. So we need to think of some strategy to tackle this limit. In this case, I think we should be able to factor both the numerator and the denominator. And hopefully, one of those factors is going to cancel. So looking in the numerator, I'm going to look for a pair where my 2 n terms multiply to give me 9 and add to give me -6. So I think -3 and -3 should work. When I add those, I'll get -6, and when I multiply those, I'll get +9. The denominator is a difference of squares, so I can factor that as x plus 3, x minus 3. Okay, and now you can see that one of these x minus 3's is going to cancel off for us, so that's nice. We're going to be left with the limit as x approaches 3 of x minus 3 over x plus 3. And now we're in good shape. I can go ahead and do a direct substitution. If I sub in 3, I'm going to get 0 in the numerator and 6 in the denominator. And that's perfectly okay. A 0 in the numerator means my overall limit should be equal to 0. Okay, so give me a moment here. I just need to sign out of my Gmail so I can get into our Math Questions Help Gmail. because I know I had a couple questions in here as well to work through tonight. Okay, I actually had one more limit to work through, so let me copy that down. So looking at this limit, 1 over x plus h squared, 1 over x squared, and an h in the denominator. So a particularly not good looking limit. And notice if we do try to do a direct substitution for h is equal to 0, I'm going to get 1 over x squared in here, and then I'm subtracting off 1 over x squared. So I'm going to get 0 divided by 0 if I do try to do a direct substitution of h is 0. So this is telling me I want to develop some kind of other strategy to tackle this limit. Maybe I can look at combining these fractions in the numerator. So what's going to happen if I try to do that? Okay, so over on the side, I'm going to do, oops, that's not what I want. I want this. Over on the side, I'm going to do a little bit of work and trying to find the common denominator for these fractions. Okay, so my first fraction has 2 copies of x plus h. And my second fraction has 2 copies of x. So they don't share any particular factors in the denominator. So that means our common denominator is going to be x times x plus h times x plus h. It's going to be these two denominators multiplied together. So in blue, I'm just going to add the 2 x's that I need to here in my first fraction, and I'm going to add the 2 x plus h's I need in this second fraction. Okay, so notice I haven't really altered these fractions. I'm just multiplying by the number 1. But this should get us closer to that common denominator we need. So x squared in the numerator and x squared x plus h squared in the denominator. Our second fraction will look like x plus h squared in the numerator and x squared x plus h squared in the denominator. So let's go ahead and combine these two fractions. We'll get x squared minus x plus h squared over some stuff. And it may not be terribly obvious where to go next, but this comes with a little bit of expertise. This x plus h squared that we have in the numerator over here, so this x plus h squared, if I were to expand this out, I'm going to get a subtraction of x squared. Okay, so that'll get rid of this x squared. And then the rest of the remaining terms are going to have an h in it. And I can factor out that h and try to cancel off this h that's inside of our denominator. So once again, I'm going to leave this particular denominator, x squared times x plus h squared, intact, but I'm going to expand out the numerator. So let's go ahead and try to fill in what's going on in our limit. So I'm going to do x squared, and I'm going to subtract, I'm going to expand out this x plus h squared. So if you expand this out, you should get x squared plus 2xh plus h squared. And all that's going to be over, my apologies, all that's going to be over x squared times x plus h squared. And then we have everything divided by h. Okay, so like I said before, these x squared pieces are going to subtract off and give us 0. So let's clean up this limit a little bit. we're going to have a negative 2xh and a negative h squared divided by our common denominator, and then divided by that lone h. Now, it might be helpful here, because there's lots of divisions happening, to actually take out this second h and write divided by h. So some students find this helpful. It kind of cleans up the limit a little bit and makes it look less intimidating. We still have a little bit of work to do. We got to factor out the h in the numerator of our first fraction. So let's factor out that h. We're going to get negative 2x minus h. And instead of writing this as divided by h, let's write it as times the reciprocal, times 1 over h. And now maybe you can see that this h and this h are going to divide out to give us 1. So we've transformed this limit into one that looks like this, negative 2x minus h divided by x squared, x plus h squared. And so now that we've divided off that h, we can look again at the limit that we have and see if we can do a direct substitution of h is equal to 0. And that should be okay. In the numerator, we will get negative 2x minus 0. And in the denominator, we're going to get x squared, x plus 0 squared. Okay, so we could write this either as negative 2x divided by x to the 4, or if you want to simplify by canceling off some of the x's, we are going to get negative 2 over x cubed. So pretty intense limit question. Let me know in the chat if you do have any questions about that one, because it's not particularly easy. So I'm just trying to find a page here of the question that I was asked to solve. So I'm looking now at number 37 on page 103 of our textbook. Okay, so number 37, page 103. And it is going to ask us if we know the following is true, that f is bounded between this line and this quadratic function, okay, anywhere x is bigger than 0, we want us to find the limit f of x as x approaches 4. So whenever I have an inequality that looks like this is telling me some information about f. It's telling me that f is going to be bounded above by this particular parabola, and f is going to be bounded below by this particular line. And let's see if I can open up Desmos here. I don't glitch out. And if you want, we could actually plot these two particular functions. So 4x minus 9 and x squared minus 4x plus 7. Okay, so just to give you some context as to what that might look like. So it looks like these functions do intersect at 4, 7. So we're going to be using a squeeze theorem kind of thing. So let's see if I can do something fancy here for you and grab this information and resize this in a nice way. So our function is always going to be bounded above by this blue parabola, and it's always going to be bounded below by this particular line. So maybe in green here, I could draw any function I want. Okay, and it can be doing kind of crazy stuff. But as we get closer and closer to x is equal to 4, it has to stay in between the blue and the red. Okay, same thing up here. It could be going as crazy as it wants, but as it gets closer and closer to x is equal to 4, it has to stay in between the blue and the red. So my guess is that the limit as we get close to 4 is going to be 7. Okay, so Desmos is going to give me that information of kind of what this function could particularly look like in green and what the sequence of y values are tending towards. So let's go back and try to prove that this limit is equal to 7. We're going to do that algebraically. So how do I do that algebraically? Well, I can actually apply the limit to all parts of this inequality. Okay, so I apply the limit to the first part of my inequality. I apply the limit to the second part, or the middle portion of my inequality, and I apply the limit to that quadratic as well. Now, the nice thing about this limit and this limit is that this line and this parabola are defined everywhere. So I can do direct substitution to get these particular limits. So over on the left side, we're going to get 4 times 4, which is 16, minus 9. Okay, and that's 7. So 7 is the lower bound of this limit. And up here, we'll get 16 minus 16 plus 7, which is also equal to 7. So we talked about this briefly in class. This is an application of the squeeze theorem. So as this quadratic, how do I put this in words? Essentially f, based on our picture that we have right here, is getting squeezed in between the parabola and the line. So eventually that limit has to go towards 7 because it really has nowhere else to go. So kind of a cool question. So thanks for suggesting to do that one on the live stream. Okay, and I think we have one more from the limit section, number 60. So number 60 on page 104. And then I'll do a little bit of work with some average values. Okay, so what does number 60 say? Number 60 gives us some information. So we know that the limit as x approaches 0 of f of x divided by x squared is 5. So this we know. And it wants us to find, or to calculate, the limit as x approaches 0 of f of x, and the limit as x approaches 0 of f of x divided by x. Okay, so what are these two limits? Whew, this is a pretty intense question. So let's try to get some information based on what we do know. So my thought is one of two things. So here's how I'm kind of thinking about this question. If I were to directly sub 0 into this limit, I'm going to get division by 0 in the denominator. So that means one of two things is going to happen here. At 0, either I have a hole in the function, or I have a vertical asymptote. One of two things. Okay, that's what happens when I get division by 0. However, our limit is actually equal to a number. And if you think about what's going to happen around a vertical asymptote, our limits are always going to be either positive infinity, negative infinity, or they may not exist if our asymptote is looking kind of like this. So the only way for this limit to actually make sense and be defined to be 5 is if our numerator, if its limit is also equal to 0. So I'm going to try to write down what I just said so you can kind of get my thought process here. Okay, so if limit as x approaches 0, or actually if we do direct substitution, right, we're going to get f of 0 over 0 in that first limit. And it's because of this denominator equaling 0 when I do direct substitution that I'm thinking one of two things. Either there's a hole or there's a vertical asymptote. Okay, so that's the information I'm getting from the denominator. However, we know that this overall limit is equal to 5. This number is not one of the infinities. So that means that f of x divided by x squared can't have a vertical asymptote at 0. It has to be a hole at x is equal to 0. Or in other words, the limit as x approaches 0 of the numerator must be equal to 0 as well. So for us to get a value, which is 5, is if our numerator and denominator are both equal to 0 when I do a direct substitution. So that's going to answer part A. So what do we need to do next? Next, we need to think about what happens for f of x divided by x. And you know what? I'm a little stumped on how to think about this one. I guess we could be a little cheeky about it. I could do something like this. So because I don't particularly care exactly what's happening at x is equal to 0, I can multiply this limit by something. And that something could be tending towards 0. So let's see. I could multiply this maybe by x divided by x. Okay, so since I don't care exactly what's happening at 0, this multiplication is okay. And then we can rewrite this limit to look like this. So f of x over x squared times x. And now we can kind of consider both of these limits at the same time. So I can consider the limit as x approaches 0 of this one times the limit as x approaches 0 of x. And we know what both of these are. This one's given to us in the question as 5, and this one we can calculate by doing a direct substitution. This one's going to be 0. Okay, so our overall limit in this case should be 0. So it looks like my feed is a little bit shaky here. So if you are tuned in, just let me know in the chat if you're having some hookup issues with the live stream. I'm going to solve one more question related to average velocity. So I just have to find that in the textbook. I think this might be in section 2.1. Yeah, so let's work through. This will be question 6 on page 82. So here we have a rock is thrown upwards on planet Mars with a velocity of 10 meters per second. And they are going to give us the height in meters after t seconds by the following function. So y is equal to 10t minus 1.86t squared. Okay, so here y is the height, and t is our time in seconds. Okay, so it's up to us to find the average velocity over some intervals that are given. I'm just going to calculate a couple. I'll do maybe 1 and 1.1. So I'll let you do 1 and 2 on your own, but I'll do part 3 so you can kind of see what the calculation looks like. And we're going to look at the interval 1 and 1.1. And we're going to find the average velocity. Okay, so I haven't really talked about physics applications yet, but the derivative of height is indeed the velocity. So all they're really asking for you to do here is calculate the slope of the secant line between t is equal to 1 and t is equal to 1.1. So let's find y at 1. That is 10 minus 1.86. Here, 8.14. And then we need to calculate y at 1.1. Which is minus 1.86 to 1.1. Okay, so here I get 8.7494. And just to try to get some accuracy, I'm going to keep all 4 of those decimal places too. Okay, so now we have 2 points, or 2 ordered pairs on our tangent line. Our first ordered pair is x equals 1, or t equals 1, and y equals 8.14. And our second point on this secant line is 1.1 and 8.7494. So let's calculate the slope of this tangent line. It's y2 minus y1 over x2 minus x1. So my difference of y's divided by my difference of x's. In the numerator, I get 0.6094, and in the denominator, we should get 0.1. So let's go ahead and divide those through. So 0.6094 divided by 0.1. Give me 6.094. Okay, so this is the slope of my secant line, or another way to talk about the slope of the secant line in this particular example is the average velocity on the interval between 1 and 1.1. So let's do one more. Let's work through part 4, just to see if we can see if there's maybe a pattern in the slope of the secant lines that we're going to get. Let's work with 1 and 1.01. And then I think part B is just asking us to estimate the instantaneous velocity, or try to figure out what the slope of the tangent line is. So we already know y at 1, that is 8.14. So now we need to get y at 1.01. So where is y? There it is. So let me put in 1.01, so 10 times 1.01. Minus 1.86 times 1.01. So here I get 8.202614. And again, we want to use these two values to try to get at the slope of our secant line. So I'm going to subtract our two y values that we have and divide by the difference of our x values. Okay, so numerator, I get 0.062614, and denominator is 0.01. Okay, for a secant slope or an average velocity of 6.26. So based on these two particular examples that we've done, I don't know if you can really easily see a pattern. At least not quite yet. So maybe let's do part 5 as well. This is the interval 1, 0.001. And then hopefully we'll get kind of an idea of what the instantaneous velocity or the slope of our tangent line is going to be. Okay, so sub 1.001 into your y function. Okay, just let me go grab that. Okay, times 1.001 times 1.001. Okay, so I get this particular decimal number. And let's go ahead and find the secant slope one last time. And hopefully we'll get an idea of what this limit is looking like. Okay, in this case, our slope ends up being about 6.27814. And so now maybe we can start to make some guesses as to where these values are going. So I'm looking specifically at, here's our first secant slope, here's our second secant slope, and here is our third secant slope. So it does look like they're getting kind of closer and closer to about 6.27 if we had to maybe make a guess. Maybe even 6.28. Okay, so that's just a guess. We just have to kind of make an educated guess based on the sequence of slopes that we're getting here. So that's probably the best we can do for part B. All right, so due to the potential of the stream maybe not syncing quite nicely on the computer, I'm going to end it here. And then we'll take a look at the video. Hopefully when the video gets uploaded later, it'll be smoother. On my computer, it's been a little fuzzy today, maybe because of just my wireless connection. So I do apologize if things have frozen a little bit, but hopefully we'll be able to follow the questions. I will come back probably on Wednesday night. I've set one up Wednesday night at 6 p.m. Okay, so you can tune in Wednesday at 6